Can you illustrate independence again on the Venn diagram?
Ah, that's a great question. I can try. Okay, so we know that mutually exclusive events can't be independent, so we know there has to be an overlap, right? The question is, how much of an overlap? It's going to look something like that. Because what has to be true? You have to have that the probability of A given B is equal to the probability of A. And this is the same thing as saying that the probability of A and B divided by the probability of B is equal to the probability of A divided by the probability of omega. So everything is omega. Yes? So the ratio of this piece to B must be the same as the ratio of this piece to the entire square or rectangle.
Okay.
But, and this is what makes it really painful, by the exact same argument, you also have that the probability of A and B divided by the probability of A has to be equal to the probability of B over the probability of omega. So if you take the intersection area here and compare that to A rather than B, that must be the same as the ratio of this area B to the entire rectangle. And that has to be true at the same time, which strains my ability to draw past the breaking point. That's the idea. At the very least, we see that there has to be an overlap, right? Yes?
That, I might be missing something, but that would mean the probability of A would have to be the same as the probability of B because the overlap has to be the same size. Am I missing it?
Yes, well, you're probably not missing it, I'm just not drawing it well.
No, I'm just trying to conceptualize the ratios.
Well, you could have something like this. A can be huge, and B can be tiny. You can still have this be true in a situation like that, but the ratios are still true.
But the overlap of the A and the B for the A would be really small and it wouldn't relate to the whole omega and A in that situation.
So here, we would have this overlap, that sliver, divided by the area of B, right? Divided by the probability of A to the whole thing.
Mm-hmm.
Yes? That's possible. It's just a question of where you put that little ring, yes?
Okay.
Similarly, when you take the probability of the overlap divided by A, here, that you're right, that would be small, but then B is already very small. Other questions? All right, I find it anyway very hard to do that, but it gives us a very handy tool because remember we already had that. Well, let me just do it all at once. We had that the probability of A given B is equal to the probability of A and B divided by the probability of B, right? By definition of conditional probability. We multiply across by B. So we get that the probability of A and B is equal to the probability of A given B times the probability of B. Yes? We're just multiplying across by B. Now, under independence, what is this equal to? No.
Probability of A.
Probability of A.
Probability of A, right? B doesn't tell you anything, so the probability of A and B is equal to the probability of A times the probability of B. And that is really the key form of the multiplication law that you tend to use all the time. And I would argue that you already knew this. Because if we had two people flipping a coin, or let's just say we had one person flipping a coin and one person rolling a die, what is the probability of getting heads and, well, first of all, what's the probability of getting heads? 50%. And a six-sided die, what's the fair die? What is the probability of getting an even number?
50%.
50%. So what's the probability of getting heads and an even number? 25%, right? Half times a half. What's the probability of getting a 6 on a fair six-sided die? 1/6. So what's the probability of getting heads and getting a 6? What's that?
1 in 12.
1 in 12. Is that obvious to everyone? So you're already using the tool, right? You're already using the multiplicative rule when you have independent events. It's just a question of formalizing it.